Hello and welcome to today's lesson on the motor effect, which is part of the magnetism and electromagnetism topic in GCSE Combined Science Physics. So in today's lesson, we're going to look at how to calculate the magnitude of the magnetic force produced on a current carrying wire. So if we've been successful and learned in today's lesson, we can describe the principles of electromagnetism, describe the effects of the motor effect, and finally calculate the magnitude of the magnetic force on a current carrying wire. So if we are successful in today's lesson, we will understand the following parts of the GCSE Combined Science Physics specification: 6.7.2.2, Fleming's left-hand rule, which is higher tier only content, and 6.7.2.3 electric motors, which is also higher tier only content. Now we can explain the motor effect as the following. Okay, consider a coil inside a permanent magnet. So you've got the permanent magnet and you've got this conductor, this coil. Now when a current flows through the conductor becomes an electromagnet. So the permanent magnet and the electromagnet's magnetic fields interact with each other. This then causes a magnetic non-contact force to be placed on both the permanent magnet and the electromagnet. Now the motor effect really only considers the forces on the electromagnet or the coil, so we'll only really now from this point onwards consider the forces on the coil, even though there's forces on the permanent magnet as well. Now as the current is flowing in opposite directions around different sides of the coil, the magnetic force is therefore acting in opposite directions on either side of the coil. So what these pairs of forces cause is they cause the coil to spin. Now a commutator is then needed in the motor to ensure the forces causing the coil to spin always act in the same direction. So it achieves this by reversing the direction of the current flow in the coil every half a rotation. This reverses the direction of the magnetic force to ensure that as the motor spins, the magnetic force stays in the same direction. Without a commutator, the coil would only spin for half a rotation. So when we consider a conductor carrying a current and it placed in a magnetic field, the magnet producing the field and the conductor exert a force on each other. Now the reason why this is because the force is caused by the conductor cutting across the magnetic field. So as a result, the magnetic field of this conductor, this electromagnet, and the permanent magnet interact with each other. So this force, like we said earlier, is a non-contact magnetic force, and the direction of this magnetic force can be determined with Fleming's left-hand rule. So in this particular example, the direction of the magnetic force is out of the screen. Now we mentioned this previously, but the maximum magnetic force is caused when the magnetic field and the electrical current are at right angles to each other, whilst there's no magnetic force produced when the magnetic field and the electrical current are parallel to each other. Now, a way to understand the magnitude of the magnetic force produced on the conductor is to consider the magnetic field lines of the permanent magnet. Now, a magnetic force is produced on the conductor when the conductor cuts through the magnetic field lines of the permanent magnet. Now, the greater the number of field lines cut by the conductor, the greater the force produced. Now, when a conductor is parallel to the magnetic field, there's no magnetic force exerted. Why is this? Well, it's because no field lines are being cut by the conductor at this point. We can say the conductor is straddling the field lines, whilst when a conductor is perpendicular to the magnetic field, there is a maximum force exerted because the most field lines possible are being cut by the conductor at this point. So what factors affect the magnitude produced by the interaction of the magnetic fields of the permanent magnet and the conductor? Well, if you think about it, it's linked to the number of field lines cut by the conductor, because the greater the number of field lines cut by the conductor, the greater the force produced. So the first factor is the magnetic flux density, or the magnetic field strength of the permanent magnet, because the greater the magnetic flux density, the greater the number of field lines cut by the conductor, the greater the force. This is because there's just more field lines per unit area. The second thing is to think about is when we consider this, is we can also state this as has the strength of the permanent magnet. Now the second factor is the length of the conductor in the field. The greater the length of the conductor in the field, the greater the number of lines cut by the conductor, because the conductor, there's more of it in the field, so the greater the force produced. And finally, the third factor is the current going through the electromagnet. The greater the current through the conductor in the field, the greater the number of lines cut by the conductor, the greater the force produced. So what equation could we then use to determine the magnitude of the magnetic force produced in the motor effect? So let's just consider the following idea. When a conductor carrying a current is placed in a magnetic field, the magnet producing the field and the conductor exert a force on each other. We call this the motor effect. And so for a conductor at right angles to a magnetic field and carrying a current, we can say that this magnetic force is equal to the magnetic flux density times by current times by length. So F equals B times by I times by L. Now the term magnetic flux density is how close the field lines are together, can also be called the magnetic field strength. Now magnetic flux density is measured in Tesla, named after Nikola Tesla, and it refers to how many magnetic field lines are found in 1 square meter. So a flux density of 3 Teslas will mean that there are 3 field lines found in 1 square meter once the field has become uniform. It doesn't get any bigger, it doesn't get any smaller. Now, once again, this equation is only true if the magnetic field and the conductor are at right angles to each other, because this is the maximum possible force produced. Now, this Bill equation, BIL, is the general equation for a large conductor found on the scale of motors. Now, the larger the magnetic force, the faster the motor spins. So this means that the larger the current through the electromagnet, the larger the magnetic force, the faster the motor spins. This means the longer the length of the electromagnet in the magnetic field, the larger the magnetic force, the faster the motor spins. It also means that the larger the magnetic flux density of the permanent magnet, the larger the magnetic force, the faster the motor spins. Now, if you wish to change the direction in which the motor spins, you change the direction of the current flowing through the electromagnet, or you can change the direction of the magnetic field of the permanent magnet. Either one would change the direction of the forces experienced by the conductor. Now, you are given this equation of F equals BIL in your examination book. You are not expected to memorize this equation, only use this particular equation. Now, the magnetic force can have an interesting effect if we place a current carrying conductor in a permanent magnetic field on a balance, which is shown in the following diagram. Now, the interaction between the current carrying conductor and the permanent magnet would lead to a magnetic force being produced. Now, remember, in this particular arrangement, it's the permanent magnet, not the conductor, which is touching the balance. So it means that in this particular arrangement, it's the weight of the permanent magnet, not the conductor, that's being measured by the balance. So remember, we always consider the magnetic force originally produced on the conductor. But like we said right at the start of this particular lesson, this also produces a force of equal size in the opposite direction on the permanent magnet. This is down to Newton's third law of motion. When there's 2 objects interacting, they'll produce forces of equal size in the opposite direction of the same type on those 2 objects. So let's consider an application of this. Let's consider that the magnetic force on a conductor is acting downwards. What would happen to the measured weight? Well, the actual value on the balance would go down, because whilst there's a magnetic force acting downwards on the wire, on the electromagnet, this means that there must be a magnetic force acting upwards on the permanent magnet, because of Newton's third law and equal yet opposite forces. Now, because the balance is measuring the resultant force downwards on the permanent magnet, it means that because there's a force acting upwards on the permanent magnet, the overall resultant force downwards on that permanent magnet is lower, so the value measured is lower. So this means that the weight of the object would appear to decrease slightly. So if the balance was at 0, the balance would read a negative value. Now, what would happen if the magnetic force was acting upwards on the conductor, on the electromagnet? Well, you would actually observe the balance to read a higher value, because whilst there's a magnetic force acting upwards on the wire, there's a magnetic force acting downwards on the permanent magnet. So that means there's a higher resultant force downwards on the balance, because the balance is measuring the permanent magnet, not the electromagnet. So this means the weight of the object would appear to increase slightly. So if the balance was at 0, the balance would read a positive number. So when a conductor carrying a current is placed in a magnetic field, the magnetic field producing the field and the conductor exert a force on each other. This is called the motor effect, and you should be able to use Fleming's left-hand rule to represent the relative orientation of the force, the current in the conductor and the magnetic field. You should be able to recall the factors that affect the size of the force on the conductor, and that for a conductor at right angles to a magnetic field and carrying a current, this magnetic force is equal to B times by I times by L. Magnetic flux density in Teslas times by current in amps times by length in meters. Now, a coil of wire carrying a current in a magnetic field tends to rotate, which is the basis of the electrical motor, and you should be able to explain how the force on a conductor in a magnetic field causes the rotation of the coil in an electrical motor. So if we've been successful and learnt in today's lesson, we should be able to describe the principles of electromagnetism, describe the effects of the motor effect, and finally calculate the magnitude of the magnetic force on a current carrying wire. So I hope you've enjoyed today's lesson on the motor effect, which is part of the magnetism and electromagnetism topic in GCSE Combined Science Physics. Thank you very much for watching, everyone, and have a lovely day.